Welcome to lecture number 2 for ECE 321 Analog Electronics, Amplifiers and Mixers. Now, in this lecture, we're going to be looking at some various op-amp circuits. With op-amps, you can build a wide variety of amplifiers and mixers. This covers some of the ones that we'll commonly be using. So starting out, let's look at the inverting amplifier. Actually, the non-inverting amplifier. Here I've got a circuit, and to write the note equations, there's a couple ways you can do that. One approach is I can say I've got 3 nodes, 3 equations for 3 unknowns, x equals Vp. Second equation I have is V plus equals V minus. And the third equation is at this node, current up plus current down plus current left equals 0. The current left is 0, so that just gives you Vm minus y over R1 plus Vm over R2 equals 0. 3 equations, 3 unknowns, solve, and eventually I get this. Now, another way to do that is to note that V plus equals V minus. So this is X, and this is X. This is a voltage divider. So X is equal to R2, what I'm measuring, over the total, R1 plus R2, all that times Y. Solving backwards, I get Y is equal to R1 plus R2 over R2 times X. And that simplifies. R2 over R2 is 1. R1 over R2 is just that. So that's another way to get this equation. Now note, with a non-inverting amplifier, the gain is always bigger than 1. It's going to be 1 plus the ratio. To see a non-inverting amplifier in action, let's design a circuit with a gain of 1.5. In that case, I want the ratio 1 plus R1 over R2 to be 1.5, or R1 over R2 is 0.5. Pick something bigger than 100 ohms, less than 10 meg. I like 1K resistors, so 1K and 500 for Y. In Circuit Lab, I can simulate that. Let's run it between 0 and 3 milliseconds with a 1 kHz sine wave. This is a 1 volt peak sine wave in Circuit Lab. Run it for 3 cycles, make the time step 1,000 times smaller, gives you 1,000 points on the plot, and let's look at X and Y. If you do that, here's what it looks like. X is right here, Y is right here, Y is 1.5 times X, and notice, X is a sine wave, Y is a sine wave. That's good. This is an amplifier. When X is positive, Y is positive, the gain is plus, and that's about it. Okay, so it's gain of plus 1.5. A second amplifier that we commonly use is the non-inverting summing amplifier. Now in this case, I can take the weighted average of 3 signals. So suppose I want to say, what's the average of 3A plus 4B plus 5C? What I can do is create a variable X. This guy right here, that's X. This is the weighted average. One way to do that is if all these resistors are the same, then by symmetry, Y is the average of A, B, and C. If I want to weigh A twice, I put 2 resistors before A, and parallel, that's R over 2. So the divider is the weighting. Weighting of 3, put 3 resistors in parallel, that becomes R over 3, and so on. So X will be the weighted average of these 3. Weighting of 3, 4, and 5 gives you 3A plus 4B plus 5C. If A, B, and C are all 1 volt, X will be 1 volt. So the denominator is whatever it takes, so that if everybody's 1, the answer is 1. And 3 plus 4 plus 5 is 12, so I need a 12 right there. So this guy right here gives you 3A plus 4B plus 5C over 12. To clear out the denominator, I throw in a non-inverting amplifier with a gain of 12. So this is 11-to-1 ratio, meaning gain of 12. That'll give you 3A plus 4B plus 5C. So in Circuit Lab, I can check that. Here's my 3 sine waves coming in. There's my summing amplifier. Problem with this circuit is if I simulate it with A, B, and C all turned on, so this is 1 volt at 1 kilohertz, V2 is 1 volt at 2 kilohertz, V3 is 1 volt at 3 kilohertz. Let her fly. So simulate. I'm going to run it for 2 cycles. Step size is 1,000 times smaller, gives me 1,000 points on the plot. Let's look at A, B, C, and Y. I don't know why I have that in there. A, B, C. Here's what you get. And the voltage at Y is the blue line. I don't really know what that's telling me. I've got too many things turned on. So to check, this is where you use superposition. Let's turn off V2. Make that 0 volts. Turn off V3. Make it 0 volts. And note, 0 volts is different than disconnect. If I disconnect, this is infinite impedance. If it's 0 volts, this is 0 impedance to ground. So 0 volts is different than disconnect. So B and C are both 0. I just have A. If I simulate it, what just happened? Okay, simulate it. I must hit the wrong button there somewhere. Now I have something. So this is the input is 1 volt. A is 3 volts. A has a gain of 3. Okay, let's turn off A. Make that 0 volts. Turn on B. Make that 1 volt. And simulate it. And here's what you get. The output is 4 volts, sine wave. B has a gain of 4. So let's try C. So turn off B. Turn on C. And simulate it. So I just clicked on simulate, run real-time simulation. There's the gain from C. Input is 1 volt, output is 5 volts. So that kind of verifies using superposition that this is 3A plus 4B plus 5C. Turn them all on and you get a mess. But that's what it's supposed to do. So that's a summing amplifier. Another way to do it is if you make the frequencies very, very different, then you can tell the difference. So if A is 1 kilohertz, this is the big outer envelope, this guy right here. This peak to peak is 6 volts. The input peak to peak is 2 volts, so the gain is 3. The inner part, the sine wave, this peak to peak is what? -7 to +1, 8 volts. The input is 2 volts peak to peak. The gain is 4. Another way to do it, another trick, if you make the frequencies different enough, you can kind of tell the difference in them. If they're too close, like 1 kilohertz, 2 kilohertz, 3 kilohertz, it's kind of a mess. It's hard to tell. But anyway, that was working. So that's the non-inverting amplifier and the non-inverting summing amplifier. Next circuit, the inverting amplifier. That's this guy. To write the equations, there's a couple ways to go. One of them, I'll write the note equations. First equation, V plus equals 0. Second equation, V minus equals V plus. So V plus, V minus looks like 0 volts. It's not actually ground. If I were to ground these together, I would get a different circuit. Remember, this has a finite gain, like 200,000. If this difference is 0, the output is 200,000 times 0. It's also 0. Actually, what it is this voltage is almost 0. It behaves like 0 volts. If the gain is infinity, it actually is 0, but you can't ground it. So anyway, where were we? Oh yeah, okay, V plus equals 0, V minus equals V plus. And the third equation, at this point, the current left plus the current right equals 0. So V minus minus V in over R2 plus VM minus V out over R1 equals 0. 3 equations, 3 unknowns, do some substitution solving, that's what you get. That's one way to solve. Second way to solve it is note that V minus is 0 volts. So suppose this is 1 volt. The current through here is 1 over R2. I'll just call it Vm over R2. It's not that complicated. That current has to go somewhere. That current has to go through here. So this is also Vm over R2. V equals IR. So the resistance is R1. So this voltage is R1 over R2 times Vm. So this point's ground. That makes the output minus R1 over R2 times Vm. That's an inverting amplifier. Example. Design an inverting amplifier with a gain of minus 1.5. So again, pick your favorite resistor. As long as the ratio is 1.5 to 1, the gain will be minus 1.5. So something bigger than 100, less than 10 meg. I chose a 1K, 1.5K. This will have a gain of minus 1.5. In Circuit Lab, I can test. Apply sine wave in, so this is x, this is y. Notice that y is 1.5 times x. The gain is 1.5, and it's inverted. When x is high, y is low. When x is low, y is high. That's the inversion, that's the minus sign. So sure enough, the gain has a gain. The circuit has a gain of minus 1.5. Variation on that, the summing inverting amplifier. Again, what I can do is write the note equations. V plus equals 0, V minus equals V plus, and this current plus that current equals 0. Gives you 3 equations, 3 unknowns, solve, and a little bit of time later, I'll get this. Another way to solve that is kind of notice that V plus equals 0, therefore V minus is 0 volts. This current is VB over RB. This current is VA over RA. Those two currents have no place to go. They have to go through R1. So that current is VA over RA plus VB over RB. That's the current. V equals IR. So this voltage is the current times R1. So it gives you R1 over RA times VA plus R1 over RB times VB. This is ground, so this will be minus that. So I get this equation. That's the summing inverting amplifier. Kind of note with the inverting amplifier, the gain can be anything between 0 and infinity. Just make the ratio. As opposed to the non-inverting amplifier, the minimum gain is 1. So there's a slight difference in the two. To illustrate that, we got a circuit lab. So here, the gain from A is 2, the gain to B is 3. If I turn them both on, again, I get kind of a mess. So let's make A equal to 1 volt. B is 0 volts. And check to make sure that the gain from A is minus 2. So I will simulate it. To simulate, run time domain simulation. Again, running for 2 cycles, 1,000 points on the plot. So here is VA in blue. Here is VB. It's out of phase, that's the minus sign. And 1 volt in gives you 2 volts out. Gain is 2. So the gain from A is minus 2. If I turn off A and turn on B, let her run, simulate, run time domain simulation. My frequency is really, really high. Let's drop the frequency some. That's why I'm at 10 kilohertz. Let's make this 2 kilohertz. Simulate, go. Again, input is 1 volt. The yellow line is V2. This is the output. 3 volts out, gain is 3. And inverted. When B is high, the output's low. When B is low, the output's high. That has a gain of -3. And if you turn both on, it's kind of hard to see what's going on. So A is 1 volt, B is 1 volt. Let her apply. By superposition, it'll be the sum of the two. And now that's the gray line. I have a hard time figuring out what's going on there, but it is the sum of the two sine waves. That's where superposition is really useful. Only use one input at a time, and you can see the gain relative to A plus the gain relative to B. The total will be the sum by superposition. So that's the summing inverting amplifier. The third one we'll look at is the instrumentation amplifier. This is kind of the great all-around amplifier. It's a non-inverting amplifier, it's an inverting amplifier, it's a differential amplifier. You name it, it does it. This kind of one circuit does everything. To analyze it, again, a couple ways to go. What I could do is have, see, I've got 1, 2, 3 nodes. I need 3 equations for 3 unknowns. First equation is V plus equals V minus. Second equation, current left plus current right equals 0. That's this guy. Vp minus A over R2 plus Vp over R1 equals 0. Third equation, current left, current right, and technically current up, but current up is 0, equals 0. That's your V minus minus B plus V minus minus R minus Y over R1 equals 0. That's an R1 equals 0. That's this equation. Do some algebra and eventually get this term. That's one way to do it. Second way. Second one's actually a bit easier, but doing the n equations, n unknowns, that always works. Might take a little bit of time doing algebra, but it'll work. A second way, by superposition, I know that the output is something times A plus something times B. So let's zero them out. Let's make A equal to 0 volts and find the gain times B. If this is 0 volts, this is 0 volts, this is 0 volts. That's the inverting amplifier. The gain of an inverting amplifier is minus R1 over R2. So that's B, minus R1 over R2. That's one term. The second term, let's let B be 0 and solve for A. Well, this is a non-inverting amplifier. The gain from Vp is Y is equal to 1 plus the ratio R1 over R2 times Vp. By voltage division, I know that Vp is equal to R1 over R1 plus R2 times A. If I rewrite this, that's equal to, putting over common denominator, R2 plus R1 over R2 times Vp. Substitute. And I get, this cancels with that, giving you plus R1 over R2 times Vp. Times A, like that. So that's Y by superposition. So the gain is plus R1 over R2 times A minus R1 over R2 times B, or R1 over R2 times A minus B. For example, suppose I want to do a straight line. Y is 10x minus 4. Again, notice it's in this form. I've got to rewrite my equation for the straight line to be in this form. So factor out the 10. Y is 10 times x minus 0.4. Matching terms, R1 over R2 is 10. Pick this to be 10 to 1. X is equal to A. Here's A. Here's B. And 0.4 is equal to B. So you can pretty much do any straight line with this circuit. This is a circuit we're going to use over and over again this semester. In Circuit Lab, I could verify that. This should be a gain of +2 times -2 times B. So checking that, let's let A equal to 1 at 1 kilohertz, B equal to 0 at 1 kilohertz, and let it fly. So I'm going to run it for 2 cycles, 2,000 or 1,000 points in the plot. And let's also look at A and B. Okay. And so here's A, there's Y. Y is +2 times A. Okay, now let's look at B. I'll turn off A. Turn on B. And let her fly. Again, it's inverted. That's the gain of minus. The input is 1 volt. The output is -2 volts. The gain is -2. So it's +2A minus 2B. And if A and B are both the same, so A is 1 volt, B is 1 volt, I should get 0 volts out. And here's the output. Turn off A and B. That's kind of hard to see. So I'll tell you what, let's turn off A and B. Just look at Y. Output should be 0. It's not. The output is actually 10 microvolts. What you're looking at is the common mode gain. A and B are going up together. Ideally, the common mode gain of an op-amp is 0. It's not. It's close to 0, but not. So instead of getting 0 volts out, I'm getting 10 microvolts out. The common mode gain is like 10 to the -5, something like that. 0.00001. It is there. Not supposed to be there, but it is there. So that's the inverting amplifier, or the instrumentation amplifier. So what we have, in summary, we've got a couple building blocks you can build with. The first one was the non-inverting amplifier. This guy. If I want a gain bigger than 1, this one does it. I have the inverting amplifier. And there's also the variation of it, the summing non-inverting amplifier. The inverting amplifier, this has a gain that's negative between 0 and infinity. Variation on it, the summing inverting amplifier, and the instrumentation amplifier. That's kind of your choice. These are the Legos, the building blocks you have for doing various circuits. If I want to build a circuit where Y is some function of A, B, C, those are the circuits you can use to build it. That's lecture number 2 for ECE 321, Analog Electronics.